How often do you take a photo and realize that someone had photobombed it? Or probably wish that if this object hadn't been there, it would have been perfect? Today, there are multiple ways to remove such objects and fill in the background details without much difficulty. But what about back in 2004? What if I told you that there was a way to extend this to videos and remove someone entirely from his or her temporal existence? Welcome everyone. Today we will talk about a research paper published at CVPR 2004 by the Weizmann Institute of Science, Israel. Space-time video completion. It aims to solve the space-time continuum equations proposed in Einstein's special, not that one. It aims to achieve space-time completion of large space-time holes in video sequences. These missing portions are filled in by sampling spatio-temporal patches from the available parts of the video, all the while enforcing global spatio-temporal consistency. This task is modeled as a global optimization problem with a well-defined objective function. This has many applications such as removing undesired objects and completing the appropriate background or correcting for missing or corrupted video frames in old videos. This is done by enforcing two main constraints. Every local spacetime patch of the final sequence should be similar to some local spacetime patch of the input sequence, and globally, all these patches must be consistent, both spatially and temporally. Let us visualize how this works. Given an input video sequence and say we want to remove her, let's mask her off and provide this as our input. The algorithm intelligently chooses different parts of this dynamic background from different frames such that overall global coherence is maintained. Simply outstanding. Now this isn't the first attempt to solve the visual completion problem. There have been multiple works over the past 5 years on texture synthesis, image completion, and image in painting, all being slight variations of each other. However, they all dealt with the same problem of global inconsistencies, as pixel editions were taken locally and independently. They heuristically used larger patches and a lot of synthetic techniques to just make it work. Also, extending these works to video is flawed as they are primarily based on smooth edge continuation, but the temporal dimension is more prone to aliasing, that is, less smoother than spatial dimension due to differences in the camera exposure time and discretization methods. Some works in video domain made use of optical flow-based methods to correct for scratches or noise, but were limited to generating small motions only. Dynamic texture synthesis was capable of generating unstructured dynamic objects such as smoke, water, and fire, but cannot model or synthesize structured dynamic objects such as people. In this work, we handle completion and synthesis of both structured and unstructured dynamic static objects, complete entire frames that never existed by spacetime patch sampling while maintaining global coherence, and provide a unified framework for image and video completion and synthesis by appropriately choosing spatial and temporal extents. And did I mention we do all this automatically with no intervention whatsoever? Let's see how. The video sequence is considered as a 3D spacetime volume where every point is identified by three coordinates x, y, and t. We define visual coherence between two video sequences as when every local spacetime patch, which is nothing but a small 3D cube, of one can be found somewhere within the other. Let S be our original video sequence and H be the hole, aka the missing pixels, aka the object to be removed. We define T as S minus H, that is the masked input video sequence, and S star as the output filled in video sequence which we seek. Then the objective visual coherence function we wish to maximize is as follows, where WP and WQ are small space-time patches in S star and T centered around points P and Q respectively, and S is a similarity function. The work considers 5x5x5 cuboidal patches WP at every point P. To intuitively understand how this equation enforces global coherence, visualize a 3D volume in which each pixel belongs to multiple patches, 125 to be exact, two of which are shown here. Now the objective function enforces that all 125 of these patches agree on the color of a single pixel, and this leads to a globally coherent solution. In case the value of P was determined locally by greedily finding the best match, it would have led to severe global inconsistencies. For the similarity function, a standard sum of square differences, mean squared error of color information, which is typically used in image completion, does not work. This is because the human eye is highly sensitive to motion, and motion continuity is more important than finding the exact spatial match. To incorporate motion information, we first find the spatial interpolal derivatives yx, yy, and yt, which is then used to find motion vectors u and v as horizontal and vertical velocities. Using these, we now define each point in the 3D volume as a 5D vector r, g, p, u and v. And distance between two patches is simply the sum of square differences of all point vectors in these patches, and this can be represented as a Gaussian similarity function between the patches. Now let's see how all these theory are put into practice. The inputs to the optimization are the original video sequence S and the hole markings H. Each point in the S-H 3D volume is represented as a 5D vector with a confidence value. Known points will have high confidence and unknown points lower. As with any nonlinear optimization, we solve this objective iteratively. The objective is satisfied if and only if for every spacetime point P, all the spacetime patches containing it agree on the color of P, and all these spacetime patches appear in the input sequence. Now these constraints can in fact be used to speed up our optimization by multiple factors. Let's say a spacetime patch WPT containing point P is closely related to another spacetime patch WT in T, then by 2 their similarity must be high, and this similarity is considered as WPT's degree of reliability. For one to hold true, the color at P should minimize the variance of colors proposed by its neighboring patches, and so the optimal solution would be to take a weighted mean of the proposals based on their reliability, aka similarity to its corresponding patch. This minimizes local error at every point while still maintaining global consistency. Additionally, this added reliability measure speeds up convergence, as patches that have reached consensus will have more influence than those which did not converge yet. To further enforce global consistency, the work also makes use of spatio-temporal pyramids, which is exactly like spatial pyramids extended to include the time axis. Thus, optimization goes from a coarse to fine level, and in each level, the best matching patches are replaced with their finer counterparts for the next level, which helps in faster convergence and preserves high spatio-temporal frequencies. Now, even a small video, say 10 seconds, may contain over 20 million spacetime points. Compare that to a standard image with 25,000 points and it is huge. To search for a matching D cross D cross D patch in T for a single point in A star, maybe over n possible patches, the complexity is of the order of D cube into n. However, as we have already established that motion measure is crucial, we don't want to fill in dynamic areas with static data. So we can use UV values of all points to find the top 1000 matching points and only compare those respective patches extensively, thus dialing down complexity to the order of n plus 1000 d cube or O of n. The crux of this paper's approach lies in its combined treatment of spatial and temporal dimensions, which although different are highly interrelated, and this relation could be exploited to speed up the computation while sometimes necessitating different treatments. For example, we have already established that temporal aliasing is much stronger than spatial aliasing, which ruled out image inpainting for video completion as it relied on edge continuity. Space-time completion, however, does not rely on smoothness of information within patches and can handle alias data much better. In this regard, the paper's approach to spatial pyramids also treats temporal dimension differently. Additionally, extending from 2D to 3D has enabled a 5x5x5 patch to provide up to 125 measurements per point, which is a lot of statistical information and leads to reliable inferences. In contrast, in 2D, this would have required the use of large 11x11 patches, which are more prone to geometric distortions and necessitates a lot of artificial correction. One may claim that this new time dimension leads to large spacetime patches and causes unnecessary increase in data complexity. However, more often than not, video data is filled with a large degree of spatio-temporal redundancies, which more than compensates for this increase by reducing the convergence time. This also ensures greater flexibility. Say there is a lack in spatial information, it can be compensated by the existence of temporal data and vice versa. That is, if the whole is spatially large and temporally small, temporal information guides the convergence. In these cases, classical image completion fails. And if the whole was temporally large but spatially small, then spatial information will provide most of the constraints. Herein, pure temporal completion fails. Thus, the unified treatment by appropriately choosing the spatial and temporal extent of holes and patches provides a great deal of flexibility. Consider these three cases. When the spacetime patch has only spatial extent, then it becomes classical image completion, but with added global consistencies which are otherwise lacking. When the spatial extent of the patch is set to the entire image, then reduces into temporal frame completion using existing frames which has been done prior. But when spatial extent of the wholes is sent to the entire image, but patches remain small, it becomes temporal completion of missing frames which may have never occurred prior, by automatically selecting bits of information from different frames and matching them coherently in space and time. Well, space-time completion is versatile for sure, but where do you think it is used? To cite a few, firstly consider video post-production. To remove static or dynamic undesired objects from video sequences, which is easier when the object reveals a background in different time senses. This approach handles even the complicated case when the background is never revealed and could even be dynamic. And did you know the variant of this work is currently being used in Photoshop as part of the content aware tool? Secondly, there is video restoration, especially when old video footage is very noisy and visually corrupted, or even entire frames be missing. These issues can be handled with ease. For example, in this Chaplin video with the splash corruption, the video is restored beautifully. It should be noted that this is one of the very early works on image and video completion, and there have been several improvements henceforth. State-of-the-art algorithms perform this much more accurately and under far less time. However, this work is much appreciated for its unique and unified approach at treating space and time as a single entity, which inspired many more to follow up with more involved algorithms. I believe these are related to Einstein's theory on space-time continuum. The links to the paper, related code base, and official website are attached in the description. If you are up for a challenge under quarantine, comment on the number of times I mentioned space and time in this video. Thank you guys for watching. Have a great day. Peace.